Okay, good evening everyone, to another episode of DanDoesData. Tonight, rather than continuing on this sort of somewhat arduous machine learning project that takes forever to train, we're going to switch tacks completely, and I'm going to work a little bit on Project Euler live. For those of you who don't know, Project Euler is a set of sort of mathematical computer science problems that you can try to solve just to sort of figure out how to solve harder and harder problems. So you learn a little bit of math, a little bit of computer science. It can be a good way to learn a new programming language as well, with a little bit of a mathematical bent. I don't recall how old it is exactly, probably like 10 years or something. I did a lot of it like 7 years ago, and I've certainly forgot a lot since then. I recall there's a strong bent towards primality testing, which is not necessarily my strong suit. So we'll see how I get through that. But if you go to projecteuler.net, you can see the front page. They keep it very minimalistic. You can register and sign in to remember which problems you've solved. I don't think that's really that big of a deal since I'm recording everything anyway. So let's just jump right into it. And yeah, they say they range in difficulty. Some of them can be hideously complicated. Let's go to the archives. This first one, and it tells you what problem number it is. The problems generally get harder as you go along. Sort of what the basic problem is, multiples of 3 and 5. So if you've been on the internet for a while, you might recall that's the Fizzbuzz problem, I believe. And it says this has been solved by 600,000 odd people. Then you go down the list, you can see how many people have solved the problem. And it drops off pretty quickly. And it would be interesting to just kind of plot how many people have solved this problem as you go along. I'm sure if you go to the last page, yes, these problems have only been solved by a few hundred people or, less than 100 people. Because it's quintinomial coefficients. Solving the quintet, very difficult. Anyway, let's jump into the first part of it. So this problem is, we want to list all the natural numbers below 10 that are multiples of 3 or 5. Oh, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all multiples of 3 or 5 below 100. So, this isn't Fizzbuzz. I lied. All we have to do is identify all the multiples and then start adding them up. So, we are here in the world of Python. This is P1. In fact, let me copy the problem statement, just so we have a standard method. There we go. So, I've just opened up Python. Eventually I might switch to Sage or something. If things are too slow and I can't find a faster solution, A, I should probably think about it harder. B, I might just switch to another language. I might switch to C, or I might redo things in C. And so you just want to find the sum of the numbers between 3 and that are multiples of 3 and 5. So if you do this absolutely naively, for I in range 1000, so all the numbers 0 through 999, 0, even if it is a multiple of 3 and 5, will not contribute to the sum, so that's not really a big deal. The most naive thing you can do is initialize some sum here, and then add to it if I mod 3 equals 0. So that is, if it's a multiple of 0, if it's a multiple of 3, do this, or it's a multiple of 5. So doing this modular operator says, hey, if I divide by 5, what's the remainder? If the remainder is 0, then it's a multiple. And that's all you do. You don't multiply otherwise. And then you can print out S. And you can see what the answer will be. So this is the sort of, let me turn on my auto indentation. There we go. I'll redo that. And you get this number. And is that right? Well, where do you publish on such and such, solved by? Do I have to log in to get the answers? To just double check? Huh. You know what? I'm not even too worried about it. So you might say, oh, it's 230 some odd thousand. Does that even make sense? So what is the sum of numbers from range 1 to 1,000? That should be 50,500 or something? No, I'm lost. 500,000. So you say, oh, it's a little under half the numbers, which that makes sense. Most numbers are going to be multiples of these. You might also just ask, how many multiples of 3 and 5 are there? So there's 333 multiples of 3, and there should be 200 multiples of 5. This isn't going to work. Is it? No, that's not going to work. That didn't work at all. No, because I'm summing up all the numbers. Right. So that's sort of the dead simplest way. And in this case, like, that's plenty fast, but how high could you go? Like, if you need to do 100,000, does this take a while now? No, that doesn't take any time at all. Also, you're noticing a trend here. 2, 3, 1, 6, 6, 6, 6, 6, 6, 8. Same thing here. So that's interesting. Also, if I'm doing the super obvious one wrong, anyone can feel free to yell at me. How bad can this be? How many can you add? Oh, now it's taking time. I'm trying to do 10 million things. So one might be able to prove that the answer will have this form. But there's only 100. Will the answer at 100 be 218? No. 2,300, 168? That might be true. 2,318. Right. Not 23,000. But if you... Aha. So do we always have one more 3 than 6? We do. 3, 6. 4 3s, 3 6s. If it's a power of 10, of course. Or is that not true? 6, 5. Well, let's find out. This is empirical mathematics at this point. I've never spent this much time thinking about this problem. Yes. So if we have... Let's go back to 1,000 here. At 1,000, we've got 2 3s and 1 8. For every 10 that we add, we're going to be adding a 3 in this, a 3 to this string, and a 6 to that string. So, result will be 2. Let's see. Log 10 of n. Minus 1. That many 3s. That many 3s. A 1. This many 6s. And an 8. So this, what if we just do 10? Is that going to be 28? 23. 23, excuse me. Yeah, they mentioned that. Okay. So that's sort of the most like obvious naive solution. And then from simple cases, you can try to build up more complex general means of solution. You could also just try to write down the answer, this sum of numbers, and then you sort of need to account for multiples of 3, multiples of 5, and then subtract. Oh, hang on. Add these, and then you don't want to double count multiples of 3 and 5. Of 3 and 5. So that'd be one way to do it. If you had NumPy, import NumPy as NP, you might think about doing this. Here's my list of numbers from 0 to 1,000 to 999 rather. If I say a of a mod 3 equals 0. Yeah, so that's the sum of all those. So I could say s equals that plus the 5s minus, we don't want to double count the 3 and 5s. 3 times 5 is 15. Oh, I can't do that? Oh, I want to element-wise add. Excuse me. There we go. Or I want to take the sum of each one of these things. Let me do this. I'll make that a little clearer. There we go. I mean, we're doing basically the same thing. In fact, we're doing slightly more computation, I think, than in the original for loop. That's a different number. Oh, it didn't actually do what I wanted. Boo. Alright, so I can't... I think it's... this is what it is. To continue a line. Nope. Just one. Okay. There we go. Yeah, same answer. But if A is, say, larger, if you've got memory to burn, what is this here? T-type equals numpy.u int 32? 32. There we go. This is what? A million? This is 10 million. I think that took some time before. This probably won't take as much of any time now. Whereas if I say 10 million here, that's 100, 1,000, 10,000, 100,000, a million, 10 million. That probably takes a little bit of time, doesn't it? Yeah. So NumPy is a whole lot faster, and you get the same result. And you get to use some of the NumPy syntax of just say, hey, pull out these indices that match this feature. And if I wanted to think about this really hard, I think you could come up with a pen and paper solution for an arbitrary size as well. I don't think I want to think about this that hard right now. I feel like that would end up being something, let's see. It's for every multiple of 5. Everything that is a multiple of 5, right? So you got the 5s, you got the 10s, you got the 15s. So it's 5 times 1 plus 2 plus 3 plus 4 up to plus whatever our number is divided by 5. Integer divide. Take the floor. So it's essentially 5 times the sum. 5 times sum of 1 to n over 5. Yeah. Something like that. Sum of I should say. Sum of doing a little bit of like latexness of I. And there are pretty straightforward, I don't know, super straightforward. There's formulas for some of the first I numbers or whatever. For like 100, for example, it's 5,050. And you can sort of think about it, oh, numbers 0 through 100, well, it's 100 plus 0 is the same as 1 plus 99. That happens 50 times, plus you got 50 in the middle. So that's 5,050. So pen and paper, you could have a general solution. Starting from this, you'd have one of these, and then you'd have one for the, it's like having one for the 5s, one for the 3s, and then you subtract the 15s. That's all. All right, I feel like that's a lot of problem 1, but you know what? I think I do want to do that. I spent all this time just thinking about it. So what is the magic formula for sum of the first I things? It is whatever I divided by 2 times, no. It's whatever I is times I over 2 plus I over 2 for even numbers. Even. For odd numbers, it's going to be, if you want to sum the numbers 0 through 99, that's going to be 4950. So that's what I need to end up with. So you just won't have that extra I over 2, is that right? But here I've got a... Yeah, because some A range, numpy dot A range of 99, sorry, 100. Yeah, 4950. Because that's 99 plus 0 plus 0 plus 98 plus 1. Oh, I guess, well, I don't have to include 0. I can say it's 99 plus 1 plus 98 plus 2, so on and so forth. So let's see. Am I not including 0 in this calculation then? There's 99 values. But I'm going to get a 49 plus a 51 plus a 50, right? That's how that would work. Right? Yeah, I mean, invalid syntax, whatever. Or the wrong solution, so to speak. You know what? I don't really have to think about it that hard. I can just say, well, just add one more number. This is so bad. Maybe I can figure it out. That is, do the I plus 1 thing, and then subtract I plus 1. Minus whatever that top number is. Boom. And then you simplify that expression. And that would tell you what you need to know. So it looks like there's an I plus 1, there's an I plus 1. So I can simplify that already. Boom, look at that. Somewhere there's a 1/2 and a 1/2 that have to cancel out. Probably more than that even. That actually sounds about right. It's whatever this is, and then you subtract out the last bit, because you have like a 50 times a 50 in the middle. Or not 50, a 50 plus 50 is sort of like the 50 pairs with itself, so you subtract out the extra bit. Okay, so def sum n of sum n. And this is some numbers 1 to n. I will say if n, if it's even, do this. Else, it's odd, so do this. Now I have to remember what the heck it was that yes, this business. So, def. The three, let's see. Multiple, whatever our multiple sum is. We need to return 3 times the sum of the numbers from n over 3, there's that many of them, plus 5 times sum of the numbers times that many of them, minus 15 times the joint sum. and divided by 15. I think that's right. Those are the ones that we will have double counted. Right, I'm taking 5 because all the numbers are 3 times whatever or 5 times whatever. I think this is right. I might need to double check this last bit here. But no, it gave me the right answer here, so I'm pretty confident. Pretty confident. Let's see what happens, shall we? Do that. And this. Alright, and then multiple of 1,000. What happens? Is your divided by 0? Oh well. Let me turn on PDB. What is N? N, oh, jeez. Try that again. Print N. 333. I don't want to take the modulo 0. I want to do that modulo 2. Even in odds, not zeros and zods. Try that one more time. There we go. Okay. That's not the right answer. It's not the right answer at all. So sum n of 1,000 divided by 3. I don't actually believe that number. No, I don't. Divided by 5, I take it? Well, I'll tell you what. I know that's always returning the same thing. That's curious. That is most curious. Did I have something like integer overflow? What is going on here? Oh, I'm using I, not N here. Change that to be I. I is just whatever the number was. There we go. This should work a little better. Yes, that is actually correct. It returns a floating point number. No, that's not quite correct. 2, 3, 4. I'm an extra 1,000 up. How do I have an extra 1,000? Oh, I added 1,000 in there. There, minus n. Right, because I'm with the numbers less than such and such. There we go. And so now we can just do this for 2,000. We couldn't do that before. It follows a different pattern. We can do this for 10,000. We can see our pattern again. And so now we can very easily test any kinds of things. And if I really wanted to think about this really hard, I could prove why you get these 3s and these 6s. That I definitely don't want to spend the time to do. We've solved this 3 different ways now of just make a stupid for loop in Python, the stupidest thing you can do. We've gone through and said, all right, well, let me use NumPy. It's at least a little faster. It's quicker more compact. And we've seen the pattern, and we saw the pattern and just sort of tried to write down the solution. And I guess there's 4 ways then. We use the properties of summing the numbers to just compute it more directly. So there's no for loop. So if we do %time it, yeah, of multiple 10 million, I said was. How long does that take? We'll see. It's entirely possible the NumPy solution is actually going to be faster, just because NumPy is heavily optimized. But we'll see. So let's try the NumPy thing here. You know what? Yeah. There we go. No, NumPy is slower. Not super surprising. And I'm not even gonna, I don't even have to use the time it module on the other one. Like this, doing one of these is slow. That takes 2, 3, 4, 5, 6, 7. Yeah, that takes a little bit of time. Whereas you notice once you know how to just compute it, it took a few microseconds. And I'm sure this could be even faster if one optimized this. You wrote it in C, you did something else like that. Then you don't need to think about it anymore. Then it's going to be really fast. Now you're probably talking nanoseconds. Things that are probably expensive here, like I'm doing floating point arithmetic even though I don't have to. Probably I could speed up these using Python or using NumPy, those kind of things. Yes, but that's the most in-depth. That was 30 minutes on problem 1 of Project Euler. I don't think I've ever spent that much time on it. Well, that's cool. All right, let's do problem 2. Okay, and let me just copy this into. I apologize for the ice cream truck noise. As soon as it starts getting vaguely warm, they are out there. They do not wait for anyone. Okay. So what do we have here? Each new term in the Fibonacci sequence is generated by adding the previous 2 terms. So you start with 1 and 2. Funny. I've normally started with 1 and 1. So 1 and 1 make 2. First 10 terms will be these numbers. So for those following along home, 1 and 2 makes 3. 3 and 2 makes 5. 5 and 3 makes 8, and so on and so forth. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, f max equals 4 million. Do not exceed. So 4 million is viable. Find the sum of the even-valued terms. So again, let's walk through sort of the brain-dead simple way to do this, and then we'll work towards the more complicated solution. First of all, we want a function to just compute the Fibonacci sequence, I think. Find the sum of the... You know what? No, let's not even do that yet. Let's just make some value, 0. Doesn't matter what it is. We'll get there. And I want to say, while f, which is the value of my current step in the Fibonacci sequence, is less than f max. Find the sum of the even value terms. Okay, so I'm going to start f at 2. It's that one. So actually I'll start s at 2. And I'll start f at 1. I'll start s at 0. I don't really care where in the sequence I am, how far along that is. But I need to remember 2 back. Curse you! F is the current. F previous is the one before that. So I would say that f comma f previous equals f plus f previous and f. So we're shifting it back 1. You could use a temporary variable just to... I'm avoiding doing that for the moment. And I say if f 2 equals 0, s plus equals f. I think this is all kosher. So I think that makes sense. 400, sorry, not 400,000, 4.6 million. Actually seems kind of small to me. Oh, but no, that's not crazy. Because what's f and fp? Yeah. Like, most of that comes from the last Fibonacci number there. We haven't kept track of, how many iterations we've done, but we can do that. I equals 0. And I'm sure we can come to a... You'll notice something interesting here. It's odd, even, odd, odd. Yeah, it's like adding 2 odd numbers, get an even number. Adding an even and an odd number, get an odd number. So there's things we can do here. Just to track how many... So there was 32 steps in the Fibonacci sequence that we took before you start getting ones that are this huge. And the sum is this number. So how can we speed this up? Well, one thing is we can write a stupid function to implement the Fibonacci sequence, to compute the next value in the Fibonacci sequence, or compute the Fibonacci, the next, I don't know, n values or something? now I'm trying to think, like, what is the best approach to even doing that? Like, you're not going to do a function to compute the next value. That's dumb, because the next value is just the sum of whatever the previous two values are. But you could say, give me like the first n Fibonacci numbers or something. Yeah, I like that idea. Fib n, which takes as argument n, and its return first n. Whoop, I need this to be a string. Return first n Fibonacci numbers. There we go. Just something like that. That's all you really need. And so, I always like to start 1, 1, so I'm going to start with that. My list, I'm not going to call it L. My list is a sequence, SQ. Starts at 1, 1. And we're returning, you know what, will we do this slightly smart? By zeros, size n. Since I know I'm going to have n numbers, I'll just do that. Yeah. And so I'll say sequence of 0 equals 1. Also, I want these to be type equals d-type, excuse me. D-type equals numpy dot u int 64, we'll say. Lots of space for these guys. 1. And the first one. Okay. And then I say for I in range 2, n, you say sequence of I equal to sequence of I minus 1 plus sequence of I minus 2. And then you return the sequence. And that's all. So let's just use that. So if I say fib n of 10, for example, I get these numbers, right? And I start 1, 1 because that's the only sane thing to do. Because you can generate the rest of them. You can't start, I guess you could start at 0, 1. Because then it's 0 and 1 is 1, 1 and 1 is 2. All right, but you can't start 0, 0. That you could definitely, that is right out. Most certainly cannot do that. So you want the terms of the Fibonacci sequence whose values do not exceed 4 million. So you'd have to say, well, hang on. I'm trying to think of the best way to do this now. Really, I want the values of the Fibonacci sequence up to size. All right. We're going to alter this slightly. Return Fibonacci numbers. Fibonacci numbers up to size n. So we don't know how big it's going to be immediately. We almost certainly don't need n values. So just for the sake of argument, suppose you don't use numpy at first. And you would say dot append. You would do this originally. And you wouldn't say, right, I don't even need an I. Just say while SQ -1 less than n. Less than or equal to? Boy, oh boy, oh boy. It's like, how do you handle this edge case? I know 4 million isn't a Fibonacci number, so I don't have to worry about it. Okay, problem solved. Because it better not be a Fibonacci number. No. No. Because F and FP are not. So we're fine. That edge case won't happen. Huzzah. While this is less than n, keep on keeping on. It's greater than n, stop. So this is going to be building a list, which is not going to be as efficient as making an array. I think you can resize arrays. Resize. But to do that every time is kind of inefficient. I guess numpy.0. No, hang on now. Let me just do this. That's 1. I'm going to try to be a little efficient here. And we won't append. I equals 0. We'll just keep count of where we are. Nope. By I equals 0, I mean I equals 2. But you say, what happens when you reach the end? Aha! In that case. Then, if I is greater than n, greater than or equal to n. No, not n. Length of sequence. There we go. Now we say sequence.resize, and we just probably want to make it twice as long as it is. So just always doubling the length when you need more. That should work, and that's reasonably efficient. Equals numpy.uint 64. Try that. You know, I did not actually read how resize worked. I should do that. The new array is larger, then the array is filled with repeated copies of A. That's not really what I want. It's different from array.resize new shape, which fills with zeros instead of repeated copies of A. Alright, that's strange. Note from the audience that there's a faster way to compute Fibonacci numbers. I'm aware of that, and we're getting to that. Sort of the goal of this is to slowly build up to the solution. If you're approaching a new problem, you're not going to immediately see what the answer is. If you immediately see what the answer is, then chances are that's really not a new problem for you. That's just an old problem that you happen to know the answer to. So we're working through slowly what the right answer is. And we may or may not get around to the fastest way to compute the Fibonacci numbers. We haven't even solved the problem for this yet. We're taking... I guess that first problem did. The first step. And that was super easy to program. But it's probably pretty slow. What was I doing? I wanted to look at how NumPy did this. Well, I got 100 things, and I say resize. What do you do? Change shape and size of array in place. Ooh. That's what I want. Oh, that's what I'm doing. Okay, perfect. So we run this. I say fibs of 10. Runtime warning. Overflow encountered. Alright, that's not good. That is not so good. Nope. Alright, tell you what. Up to size n. Right. Let's just set this. And let's just walk through what this should be. I want to find... I don't want to return the whole dang thing. Resize I think that's what I want. Yeah, I think that's right. I'm having like a strange sense of deja vu now. Like I've already solved this kind of thing before. Not on stream, but probably like years ago. I equals 2. What is the last entry? Oh, I can't use that now. No, that needs to be I. There we go. No, it needs to be I minus 1. One of these days. One of these days, man. If the previous entry that we did. Yes, that is 1. N is 10. Life is... Okay, now what's SQ? 1, 1, 2. Yes, that's correct. So we will increment I. And, oh, I don't want the length of the sequence. No, yeah, that's true. I need to ask, is I greater than or equal to the actual length of my sequence? And I say, no, it's not. So that's fine. Life goes on. Now the previous entry. Now I is 3. You can check this again. You ask, is that less than n? It is. You keep going. You set this. You set this. Take a look at the sequence. Just take a look. 1, 1, 2, 3. Yep, that's all. Everything's hunky dory. That's still way less than what we've got. Do this again. 2, 3, 5. Turn Fibonacci numbers up to size n. Yes, that is correct. And I'm saying n is 10 here. Let's do that. And yes, 8. And now, alright, but now it's at 13. Oh, well, it wouldn't have. I see. I see. So I'm going to end up computing that last one. I will end up computing the last value, and the last value is the one that put me over this I minus 1. So I don't want it in here. So I don't know what the heck went wrong here. Everything seems kosher to me. Yeah. Yeah, that was all. I don't know what went wrong there. 12. 13. Not until I say 14 do I get that next value. Oh, and because I've got a double-digit number here, it's got to reserve that much space for each one. That's kind of interesting. I did not know NumPy did that. I just never noticed, I guess. All right, so now we can compute the numbers up to size whatever. We wanted 4 million, right? Boom, there they are. There's not all that many of them. And then you say f of whichever ones are even, and you take the sum of them. And I believe that's the number we got before. We can double check. Always important to check. Yes, same number. So we've done this one 2 different ways now. Now, as was mentioned in the audience, there are faster ways to compute the various Fibonacci numbers. And in this particular case, you don't even really... It's like you only want the even numbers, and you can identify which ones are the even numbers, in fact, ahead of time. So if you call it... Well, you know what, I'm just going to put the 1 there. The first 10 terms, you know, for whatever, first 11 terms. It's all 0 up counting, 1 up counting business. You note, this 2 is even, and then you go to a 3 and 5, then an 8, then a 13 and 21, then a 34. It's every third number. And as I alluded to earlier, the reason for that is, well, you start with an odd and an odd, which gives you an even. Then an even and an odd gives you an odd. Then you have an even and an odd again, which gives you an odd. But now you've got 2 odds, which gives you an even. Sort of like the old bad proof that 2/3 of all numbers must be odd. So this step I could speed up, in fact. If I've generated all the numbers, or I have some means of generating a particular number, I don't actually need to generate all of them. So in fact, let's... that's not going to take any time. Let me add, like, 2 to that. This is still nothing. Yeah, so 10 microseconds versus, I know I only need to take every third one, starting with the second one. fast is that? Twice as fast. Why? Because I don't need to do all these tests. I just have to pull out things. So in an ideal world, yes, it would be take 33% as long. But not quite that ideal, because you still have to extract them in this fashion. So that's kind of cool. And I don't think I'm going to go into, like, oh, how do you generate Fibonacci number n? I guess we can look on, when you're not sure, often what you might do is look on Wikipedia. You might try to find a particular method for how do you generate the nth Fibonacci number. So if you go on there, Fibonacci numbers, sequence, Fibonacci series, excuse me. Number, sequence, series, whatever. Yes, often, oh, see? It's extended by one more initial term, the zeros. I knew it. Yes, here's a good visual. You get this cool looking spiral, stuff like that. Yes, as I mentioned, they start with this recurrence relation. That's sort of the way we've been computing them, which is sort of linear in time. You got to do one operation to get the next step. So it's order n. If you wanted to closed form expression, that's sort of the... it's almost always the fastest way. And you think, oh, great, I'll just do this. Where phi is some goofy-ass ratio. Well, you know, the thing is... Oh, it doesn't exist? Oh, I totally thought it would have had that. I really thought it. Hang on. Is it in here? I thought it might be in here. Pi is, but not phi. Oh, well. Like every sequence defined by a linear recurrence with constant coefficients. Did not know that. Must have a closed form solution, known as Benet's formula, even though it was known by de Moivre. That's interesting. Oh, there's a phi and there's a psi. I got myself all mixed up. So you could just compute the answer, snap your fingers, and compute the answer. However, doing these kinds of operations might be mildly irritating. Using mathematics. Yes, so this is a faster way to sort of compute these numbers. This is the like log n solution. It's shallow diagonals. That's such a weird graphic. It's like, I guess it's the number, and then whatever number is next to the left, but you skip down one and to the left. You skip one. Nutty. Oh, which is this in Pascal's triangle. Oh, that's cool. So yes, you can read all about how you can solve the numbers. Oh, there's negative description. That's super cool. That's neat. And it goes on and on. You can find all kinds of stuff here. So, but I don't want to go all into that. This is not strictly speaking a math show. Let's just spend a little bit of time thinking about this problem number 3 here, which is our first like primality tester, which is going to be another set of very typical problems for Project Euler. So they just briefly describe like what are the prime factors of this number. FYI, for you if you don't know, if you've got a number like 21, that's 3 times 7. We say that 3 and 7 are the prime factors. And they are prime because no other integer will divide them evenly. Excuse me, no other natural number will divide them evenly, just themselves and 1. So starting at 2, 3, 5, 7, not 9, but yes, 11, yes, 13. So those are prime numbers. There's very popular in mathematics, they come up all the time. And they're saying that, hey, you've got this 13,195, its factors are 5, 7, 13, and 29. What's the largest prime factor of this number? So this is a sort of factor the number, and then tell me what the largest one is. Now, in theory, you don't have to factor the whole dang number. But you can see right away you're probably not going to do this You're not going to do this naively by hand. How do you do it naively? Well, let's find out. So n is whatever this number is. Let me copy that. There we go. And there's no numpy dot is prime. If you use Sage, there definitely is an is prime. You can sort of get away doing that. So we're going to have to write some kind of function, A, to probably check, is a certain number prime? And B, what is the prime factor? So we want to find we need to find a way to break down, to factorize a number. That's sort of the obvious thing that you need to do. I'm surprised the question isn't just like, is such and such a number prime? That's kind of funny. So, let me think about this. The prime factors. The prime factors of a number are no bigger than the square root of the number. So if you're dealing with like 64, that's a square number, because 64 equals 8 times 8, right? Yeah, sure. Can't assign the rule. No, that's fine. Equals, 8 times 8, yes. Whereas if you had 65, that is equal to 5 times 13. So the factorization is larger than the square root. All right, I was trying to convince myself. of that. But if one of the factors is bigger than if a number has only two factors, and one of them is bigger than the square root of the number, just to make our lives simple here, then the other one must be smaller, and so you will have found it first. But we really want the biggest number is the thing. So we could, I want the biggest number. So I could start. No, I'm not going to start there. I will have to think about this. The answer should be obvious, you know. So the slowest, stupidest thing would be to check if every number is a divisor. And then check each divisor for primality. So I think we can implement this super stupid solution. And we're going to start out ultra stupid. We're going to check all the even numbers too, just to be dumb. Just to be very explicit about what the heck it is we're doing. And I'm not going to stop at any particular point. You should stop at, you should, no, we're not stopping anywhere. So for every number, starting from 1, starting from 2, you can at least only worry about, I know it's not 1, but the largest prime factor of the number, such and such, such and such. It might, because the number might end up being itself, right? If it itself is prime, then the largest prime factor of the number will be the number. So if I need to check if it's a divisor. N divided by I, is that what I'm looking at? N mod I, right. That's what I want. So divs is just some list. And we'll say divs dot append fine. And then we need to test if each divisor is prime. And so there's lots of ways you can do this. We want to check the absolutely positive, stupidest way. Check if each number is divided. Yeah, that's fine. So let's do this. Did I never set my n. There we go. Doink. That's taking more time than I want. tell you what, let's do their short version, 13195 first. Yes. So these are all the divisors of that number. But you'll notice there's a lot of extra numbers in here, numbers that are not prime. The largest prime is 29, which is in our list. We just have to suss out where the number is. And so the stupidest thing you can do is test whether each number of the in here is prime. What you're going to see is that all of these other numbers are multiples of the primes. So 35 is 5 times 7. 65 is 5 times 13. I bet 91 is 7 and 13. 145 is going to be 5 and 29, I think. Yeah. So, working their way up. And I bet 13 times 29 is 377, is in the list. Cool. So, we're going to make it as stupid as possible function. Is prime. Yeah, we'll just call it P for potential prime. We'll say stupid primality check. And there's, as I said, lots of smart ways. We are just going to implement the stupidest possible way. And you do only go up to the square root of P. But you know, that takes a long time to compute, so we'll go up to P over 2. That's fast enough, right? You only go up to 2, and we'll say P over 2. And we will, first of all, we'll do the next to stupidest thing. I'll say if P mod 2, if it's even, just return false. It's not prime if it's even. So then we can start at 3. And every time I just check if P mod I, if it is divided by this number, then we return false. That's all. If we make it all the way in, we return true. That is prime. This will work. It's just going to be slow as all heck. So is prime 3. Is prime 2. Alright, that's one little check here. If B equals 2. Return true. Because 2 is technically a valid prime. Is prime 2, 3, 4, 13, 195 is false. Okay, perfect. And then we just say so P's is going to equal D for D in divs if is prime D. And then you say numpy.max of D. D is not defined. P. P. There we go. And so that's the stupidest possible thing you can do. And I'm already a little over time, but let's see if we can, how long it will take to do this outrageously huge problem. How long will it take to compute all the divisors of this problem? Oh my goodness, that's so long. Ain't nobody got time for that. Ain't nobody got time for that. In fact, from TQDM import, let's get a progress bar. TQDM, let's see how bad it is. Probably eating up memory too. Oh yeah, this is gonna take an hour to do the stupidest possible way you can imagine. So that's not going to work. Just so everybody's clear. Like all these problems should take, I think, at most a couple minutes to solve. on a standard desktop computer using something vaguely intelligent. And a large number of problems can in fact be solved with pencil and paper. So I'm actually not even going to let this run and finish. And there's no reason for you to wait an hour. But we might look at that next week. We might move on to another problem. This is just showing the stupidest possible way to solve this problem, whereas we went into a little bit more detail of some of these earlier problems. So again, that was just some Project Euler stuff. I hope this was helpful to people. I kind of like it, just kind of working through these. It exercises my brain a little bit. Lets me get familiar with Python. I might redo some of these solutions in like C or Fortran. Yes, these are all still pretty basic, but often working hard through the basics can be really helpful. All right, that is all I got for tonight. So I want you all to take care, and don't forget, stay safe in the data mines. Have a good night.